Hello, I'm Nicole Sultanum, and on behalf of my collaborators, I'm going to present my internship project at Microsoft Research titled A Teaching Language for Building Object Detection Models. I believe I don't have to convince you of what a tremendous resource machine learning is in its ability to automate a variety of tasks. But you will also agree that it can be really hard to get a model up and running. Given the complexity of the space, the limited expert pool, and particularly in some domains where label data is scarce, requirements change often, making the process really costly and time-consuming. An approach to make this process less painful is a vision called machine teaching. It is about making the training process more like a teaching process, where a human poses as a teacher to a computational learning system. This happens via a rich interchange that transcends traditional label-based learning and includes higher-level semantic constructs like features and schema. As for what these mean, say you want to teach a learning agent to recognize apples in images. Teaching via labels would consist of showing lots and lots of examples, whereas teaching with features would be more like telling it to pay attention to color and shape as key characteristics of apples. And schema is about constraints and relations, like that apples have stalks and sometimes a leaf attached to said stalk. Teaching-based models don't quite exist yet, but this idea of a rich interchange is really promising if you consider it may help support and expedite learning by leveraging prior knowledge. And then the next question is, assuming the technology existed, what would this interchange or language look like so as to comfort enough expressivity to teachers in communicating what they need? And how do you design an interactive experience around a learning system like that? And perhaps more importantly, does this whole teaching idea make sense to people? We set out to answer those questions via two exploratory studies in which we emulated the experience of teaching a learning system. Among the many machine learning tasks we could have chosen, we picked object detection, which is a richer, more generalizable problem than classification. So for our first study, we recruited 12 participants to play the role of teachers to a hypothetical learning system which we called Pixie. Communication with Pixie was mediated by a human interpreter, the facilitator of the study, and participants were told the system could understand anything that the interpreter could, be it speech, sketches, gestures, and so on. This entity separation was to encourage participants to consider the computational nature of the learner while still allowing for a full range of expression. We then gave the participants one target concept out of these three and asked them to explain to Pixie how it can recognize instances of said concept in images within three different contexts. We first started with a really open-ended prompt, asking them to freely explain the concept to Pixie. Based on their responses and any new concepts introduced, such as racket in this example, Pixie could ask for more details from a small scripted list of possible questions. Then we gave them image printouts and asked them to identify the target concept and what elements in the image justify that decision, using a set of positive, negative, and borderline examples. We then did the same but with examples pre-labeled by Pixie and asked them to judge the quality of the labels. At this stage, participants could also ask Pixie what other things it recognized in the image, like rackets or tennis balls. These three tasks helped inform explanation patterns as well as lots of concrete explanation samples for analysis. To start, we found that explanation workflows were pretty consistent across participants. They generally started their explanations covering the general case and then expanded it to cover edge cases. But then, working with images was really helpful to recall these edge cases and contextualize descriptions, particularly so for concepts that are hard to explain, such as aesthetically pleasing or the notion of round. We also identified a few building blocks for explanations, including concepts, or anything in an image that can be outlined, attributes, which are properties of the things you outline like shape, color, size, relationships on the interplay of two or more concepts, and something we call qualifiers, which modulate the meaning of other building blocks in different ways, such as an indicator of uncertainty or frequency, cardinality constraints, and so on. And lastly, findings underscore the importance of dialogue that allowed participants to gauge what the system knew or didn't know, and there was also an expectation that learner feedback be provided in the same language used by the teacher for explanations. So, we summarize these findings via a set of design goals, including a minimal but expressive set of language constructs, working with image samples, supporting a two-way dialogue, and providing awareness of the learner's knowledge and progress. We applied these goals to create a design pro for Pixie, used to reassess the teaching experience in the context of a real computational tool. For a more believable experience, we used two off-the-shelf object detection models to generate predictions. I'll demonstrate a workflow from scratch for someone teaching the concept of person riding bicycle to Pixie. After typing out the target concept in the respective box, Pixie does a search for images to help contextualize teaching. Pixie's prior knowledge is provided via a pre-trained set of common concepts, like person and bicycle, shown here as white dashed boxes over the images. After getting acquainted with what concepts the system knows, the teacher may choose to use them to teach new things about the target concept. In the concept descriptions box, teachers can input expressions based on a subset of our identified language constructs. They can define standalone concepts, as well as relationships between new and existing concepts. They can also attach optional qualifiers, such as uncertainty or cardinality indicators. And existing concepts listed in the concept descriptions box, like person and bicycle, are now shown blue in the center image. Pixie happens to know what a person is, but not helmet or wheel. For these concepts, the teacher needs to provide a few examples before Pixie can start predicting them. Teacher-provided labels are shown with a solid outline versus Pixie predictions, which are shown with dashed outlines. The teacher can provide feedback to Pixie on its predicted labels by confirming them, which turns the dashed outlines into solid outlines. And this is how relationship labels can be added. Before moving away from this image, the teacher adds a label for the target concept itself, which is shown in yellow. As the teacher continues to work on other images, the learning panel updates with the number of labels added, confirmed, and removed by the teacher, and how often these labels appeared with the target concept. As for this indicator, it shows how many labels Pixie needs before it can start making predictions about that concept. After we add one more label for helmet, it will start the training process. After that's done, Pixie will start showing helmet predictions in images. Teachers can further test Pixie on how well it's doing with helmets. Pixie samples new images where helmets were found, so the teacher can inspect and further refine Pixie's knowledge on that concept. Moving on, we wanted to see how teachers appropriated the teaching experience enabled by Pixie. We recruited 8 participants to teach it the concept of person riding bicycle within a 15-minute think aloud session. Participants were told, in general terms, that the system would take everything they taught into account. Please check our paper for a detailed coverage of findings, but here's an overview of how they informed our research questions. Starting with how teachers understood and used the teaching language. After a bit of guidance, participants grasped the mechanics of teaching in the language, saying the experience made sense and was more substantial than they expected. But many also found it surprisingly challenging, as they realized that even a concept as simple as a bicycle can entail a lot of nuance and ambiguity, with different ways to decompose a bicycle and link them to a person. As such, having means to change and experiment with explanations mid-teaching is a really important next step. Some of the challenges they faced were also due to limitations of the teaching language. While we purposefully kept our concept description simple to avoid overwhelming teachers, they craved more expressive power. They wished to describe attributes and states, exclusive classes, things to ignore, and so on. As such, it's worth expanding the list of language constructs while managing complexity of the language. As for system-wide considerations, we found some support for the notion of a shared language as participants took naturally to teaching labels and learner predictions coexisting in the same image. Regarding the use of bounding boxes for labels, they were simple to create but made concepts like road and sky much harder to annotate. Other labeling modes should be assessed for expressivity. And finally, teachers wanted to know how their teaching affected learning. We argue language constructs could be used here for explainability, for example, indicating how each concept description has contributed to a particular prediction. To wrap this up, this work has looked at how human teachers may teach computational learners using a teaching language. We found the concept is viable and mapped out several directions for follow-up work. And that's it. Thanks for making it this far. Here's our contact information if you have any questions, and stay safe.